Okay? So we didn't really use the free body diagram for the previous case. We will now because we have to find the friction force. Free body diagram helps a lot when you're finding your friction force. But it doesn't hurt because it helps you to see how the, which forces are acting in which direction, make sure you kind of account for things properly. So the free body diagram is usually a good start. So let's do that. Free body diagram. As it's going up the incline. Surface is touching it. Surface can interact in two ways, through a normal force and through a friction force. We have a pulling force. We have a spring. What else is touching it? Touching. That's it, right? And then we have gravity, mg. I think that's it. If you'd like to, you can. It just, whatever helps. So if you are finding, in this case, we're not using work done. If you were using work done, you could use this angle then, right? I'll call it this. So the work done by gravity would equal mg times d times the sine of that angle, right? Sorry, cosine of that angle. Oops. And that would give you a negative sign, and it would all work out just nicely. Or I kind of just like to use the components for it, but in this case, I think it's okay. But we're not using the work done by gravity. I think it's okay to draw it like this. Do a few problems and see what helps you the most. All right, so we're ready to do our energy conservation equation. And again, you can go back and try the work approach. Find the work done by every one of these forces. Add them all up. The net work has to equal the change in kinetic energy. See if you get the same answer. You should, right? So let's go ahead and do it this way. And you don't want to forget something, you don't want to miss something. So especially, when you're first starting out doing these problems, just write out the equations. I always like to say, start with something on your paper that's correct. Makes it a lot easier to give partial credit when there's some starting point that's right. So just write out an equation and then start filling things in. It's often, you'll catch yourself as you're doing it. You won't forget to square something. If you write out the equation properly, it's there, and then it's a reminder as you fill in numbers not to forget to square the distance for the spring energy or something like that. Okay, so what do we have? We've got a kinetic energy, we've got a gravitational potential energy, and a spring potential energy at the beginning. And we've got kinetic, gravitational potential, and spring potential energy at the end. All right, so there's our equation. So far, we're pretty much the same as we were last time. And I'll go ahead and, what do I want to do here? I'll just fill in. Well, we know we're starting with no kinetic energy, right? We good with that? We know we can define either our beginning or our final height to be 0. Oh, what would happen if we defined our final height to be 0? What would our initial height be? Negative. because when something moves up, its gravitational potential energy has to increase. When something moves down, it has to decrease. And if it if it ends at 0 and it's moved up, it had to have started with a number smaller than 0. Okay? That's okay. You can do that. We can have negative potential energy, gravitational potential energy. But just make sure you get that right. You can pick any place to be 0, but make sure your gravitational potential energy goes up when your elevation goes up. So usually we pick the lowest point to be 0, but it's not necessary. So we'll pick the lowest point to be 0 in this case. And the spring starts out at its equilibrium length, okay? Now we're ready to fill in. Nothing else is 0, right? Okay. Work done by the friction force. That's going to be negative the friction force times the distance. You good with that? Okay. That's that. And then the external force is going to be the pulling force times the distance. That's positive. And that's going to equal 1/2 mv squared mg y final. What was y final? D sine theta. And our spring potential energy, 1/2 k d squared. D is the distance it's moved up, right? 1/2 kx squared. X is equal to d, the distance up the incline. The distance the spring has stretched. So all the same as the last time except one new term here. Friction force times the distance. What is the friction force? Don't forget to multiply it by the distance. A lot of people forget the distance there. Friction force times the distance. The friction force is mu times the normal force, mu sub k times the normal force. And the normal force we get from our free body diagram. This is where you may want to break up that weight into components, force of gravity into components, because the friction force, I'll do that here. Normal force, pulling force, that's mg cosine theta. That's mg sine theta. That's F spring. That's Fk. I've kind of drawn different lengths so I can get all the letters on there so we know what they are, but the lengths aren't accurate at this time. I didn't calculate those forces. I'm not sure if the lengths are proportional to the magnitudes or not. Okay, so what is my normal force? It's mg cosine theta. We good with that? That comes from the sum of the forces in the y direction have to be 0 because it's not moving in that direction. So the normal force equals mg cosine theta. All right, now we plug that in, and what do we get? Got a minus 0.2, 5, 9.8 cosine 30 degrees. D is 1.2. And what was those numbers? Those were 90. Okay, if I did it right last time, those numbers should be the same. And what do we get? 30. This is 10. 10.2. Hope it makes it.